Thank you very much. I am Mathieu Bacou, French researcher from Télécom SudParis, also from Institut Polytechnique de Paris and INRIA. And actually today I'm representing a consortium of 11 researchers and PhD students working around a French government-funded research project that is called MapRenum. Our goal is to make one machine out of many, and as the subtitle suggests, we want to add 64 more bits to RV64. And what you are going to do with that, you will see in this presentation. In our consortium, we have both hardware researchers and operating system researchers. I am one of the latter, so sorry for being a bit approximate on some hardware parts. But this capability to co-design on hardware and on software, we want to use that to address the problems in high-performance computing and also on cloud computing of distribution and heterogeneity. And we want to do that through this 128-bit architecture. If we have a look at here for the high-performance computing on the top 500 machines, we can see a trend towards even more parallelism and distribution to scales that we have never seen before, of course. But also we have a trend towards heterogeneity with the introduction more and more of accelerators of all forms, GPUs, FPGAs, and so on. So it all makes this machine very hard to program and to use efficiently. And we do want to develop this vision of an HPC machine by 2030 that will, of course, we need more than 64 bits to address all the hardware capabilities of the machine. And you can see our quick calculation here. We can imagine clusters at the scale of million with each hundreds of cores and terabytes of memory. We will need more than 64 bits here. And the challenge here is how to make RISC-V able to take advantage of this machine, and the other way around, how we can take advantage of RISC-V and RV128 specification to first manage the heterogeneity of the machine, then to optimize and simplify the operating system stack, very important for us to be co-designing all of this, and finally, of course, the goal is to always increase the performance of the distributed computing we have here. So I'm saying that we will need more than 64 bits. Let's be honest, we will eventually end to 1 and 28 bits flat, and we should target that already. Of course, this hypothetical machine will only arrive maybe in 10 years, but we want to be there and to be a strength of proposal to the specification of RV128, because we want to be able to express what we need from the architecture and what the architecture will need also. So let's see, let's have a look at a few opportunities and challenges that we see for RISC-V and 128-bit architecture. This is only a few, of course. It's but one research project. Of course, you are all welcome to come see me at my poster to discuss all about that. Obviously, we have two main axes that we present here. First, on the architecture and microarchitecture side, we are asking ourselves what could and should change if we have 128-bit addresses. Clearly, we would like to allow for disaggregated hardware. In one single rack, for instance, have dedicated hardware just for computing, just for memory, just for accelerators, and so on. We want this disaggregated hardware to be used as a single system machine using RV128 as the common denominator to write software. And a second challenge in this axe of architecture and microarchitecture is that probably we don't want to just double the breadth of the path in the microarchitecture. Even I, as a software researcher, I know that. But RV128 doesn't mean that all the computation will be 128 bits. So presenting that, I will be very quick on this illustration. You can, again, see it better at my poster at the O4 afterwards. But indeed, we state that most 128-bit computations will actually manipulate addresses. So this is an opportunity to develop a clustered architecture. So you will have in front a dynamic steering logic in the hardware to decide whether to dispatch an instruction to a cluster to compute well addresses over 128 bits, or computation is actually over this number of bits. But you will also have the normal integer computing cluster at 64 bits, and then of course your floating point and SIMD cluster at over even more than 128-bit as usual. A second idea going through this slide here is that we will probably be able to compress a lot the pointers that will be over 128 bits. The software will be able to optimize the memory placement, the layout of the memory, to make great use of cache compression to be still efficient. Now, on the operating system side, we are asking ourselves what should and would the operating system over 128-bit look like, and hopefully it will be different than the 64 bits one. I say hopefully because I want things to be a bit exciting. And here we are proposing to redesign the operating system instructions, many of the process, and we want to incorporate the hardware-assisted virtualization in the way we provide interfaces to the processes. And to achieve that, we state that we want to access to access all the hardware through one unified 128-bit address space. So this is an example. Again, please come see my poster for more details. You can see if we have two machines that are actually different, one being for the compute side with, for instance, a Java application running on machine A, and then the machine B could be a memory node, that is to say only providing memory resources and almost no computing resources. We can see that we could dispatch efficiently some applications. So there is interest with that with the Java virtual machine for performance that I can detail here. And having the capacity to disaggregate the software, that is to say the Java application, between the compute node and having the garbage collector on the memory node will make things very efficient and easier for the software developer. And it can all go through this unified 128 bits memory space that you can see will span all the machines, or the accelerators, or also the specific types of memory. As you can see, I'm talking about persistent memory here. We have many, many ideas, even more than I can present here. I talked about the Java runtime. You can also see that we want to leverage the capacity of the user space process to manipulate its own memory space to have a tailored NUMA placement, non-uniform memory access placement for best performance specifically designed for this application. And as for the persistent memory, it's always a hardware feature to use on the software side. The libraries are not very helpful to the developer. You have to use specific data structures. Here, we have the ambition to make their utilization transparent through this unified hardware virtualized memory space. And more than the ambition, we have that in development with our PhD students. So wrapping all that up, for us, both on hardware and software sides, RV128-bit is an opportunity for co-designing all the stack. And I want to focus on the fact that for us, the issues and the opportunities are not just on the ISA extensions, but also on parallel and distributed aspects of the architecture. You can see that because we are targeting making a disaggregated operating system over this unified address space, and we want to enable a common general-purpose 128-bit architecture to better use this heterogeneous hardware. So of course, those machines we are targeting are probably quite far away, but this work will take a lot of time. We're starting early, and hopefully we will continue doing that for quite a long time. RISC-V is very exciting for all of us, and I'm glad to be here today. So thank you very much, and I probably have some time for questions.
Thank you, Mathieu. So Mathieu has a poster outside. I have so many questions, it's not true, but I ought to give everyone else a chance. Questions for Mathieu? Stunned silence. OK. First question. I'm a software engineer. Before silicon, I have to emulate it so I can develop software. How do you emulate such a massive machine?
Yeah, so thank you. So obviously, for the hardware part, I can't exactly answer. You know better than me how you can do that. But for the software part, we are using hardware virtualization also both as a solution, as I mentioned, but as a mean of development. And of course, we are running all that on QEMU. We do have support for 128-bit instructions and also compiler support in GCC for those instructions. And about the NUMA architecture, we also use that to simulate the disaggregated giant machine that we are targeting.
Thank you. Second call, any questions? I have another question. Yes, in the middle.
Thank you for the presentation, Mathieu Bacou from the CA. How you manage to maintain coherence in memory in such a wide and distributed system?
Yeah, this is something that I glossed over a bit. We are hypothesizing that the CXL protocol and hardware will arrive and will enable us to actually don't care too much on that. That's one part of the answer. The other part is that actually we want to leverage the difference in memory coherency on some part of our work. Things I hid when talking about my disaggregated Java virtual machine is that we are using the difference in memory domain coherency between the garbage collector and the computing application to avoid costly synchronization between both.
Okay. Any other questions? I have a technical question for you about the standards. Within the encoding of the RISC-V ISA, you have 32-bit instructions and potentially bigger instructions. Within the 32-bit encoding of the 32 groups of instructions, 4 are reserved for vendor relocations. Mm-hmm. 2 of those are actually vendor relocation stroke 128-bit. Have you thought how you're going to deal with the fact that when you get 128-bit architectures, you're going to start to get code clashes because the architecture is trying to use the same encoding for 2 different things?
Sadly, I probably won't be able to answer that, sorry. You'll have to ask my colleagues on the project on this hardware parts, I'm sorry.
Okay, more generally, how are you engaging with the RISC-V international community to take RV128 standardization forward?
For now, it's a bit early in the project to propose concrete things. We are still in the process of developing that in our research labs. We are close to publishing our first ideas, and then yes, of course, we are going to commit back to the community. We have in the project involved. I can show again. Yeah, it's slow. The people involved, but we have people involved in the project and also in the RISC-V community actively, so you will hear from us in probably the next year.
Okay. Mathieu, thank you very much.
Thank you again.